Okay. Hi everyone. Apparently people don't want to come after midterm exam. I don't know. It's a bit weird, but what do I do? There is Ghazal also online, so only you two are here in the class. Okay, I will teach. So what it covered so far, last session we talked about MDS and isomap, salmon mapping, and before that we covered PCA, FDA, and these things. So many of the spectral dimensionality reduction algorithms were covered. Now we are going to continue with that approach. Local linear embedding is another spectral dimensionality reduction algorithm. Afterwards, we will talk about t-SNE, variational invariance and variational autoencoder, which can be seen. Sorry, variational invariance and factor analysis and probabilistic PCA. We're going to talk about them, which are probabilistic dimensionality reduction algorithms. And then afterwards, we're going to cover t-SNE and UMAP, two state-of-the-art algorithms for data visualization and dimensionality reduction. They are probabilistic methods. And then we'll cover HMM, hidden Markov model. Okay, so local linear embedding, or LLE in short, it was proposed in the year 2000. It was this paper and isomap paper were back-to-back, were published back-to-back in Science Journal. So they were breakthroughs. It is a nonlinear spectral dimensionality reduction method. What do I mean by spectral? It means that they have spectral dimensionality reduction algorithms. They have geometric approach perspective, and also they usually reduce to eigenvalue problem and generalized eigenvalue problem. Okay, so it can be used for manifold embedding and feature extraction or dimensionality reduction. Okay, LLE tries to preserve the local structure of data in the embedding space. So many of the dimensionality reduction algorithms do that. This actually, this idea was proposed by LLE, and most of the especially unsupervised dimensionality reduction algorithms follow that approach. They say, let us fit locally, but think globally. So that's the main idea of many unsupervised dimensionality reduction algorithms. They say, let's fit locally. What do I mean by fit locally? I mean, if 2 points are close to each other, they should also fall close to each other in the embedding space, right? So so we try to preserve the similarity of close by points in the embedding space. Hopefully the global structure will be preserved by doing this. So fitting locally and thinking globally. This is the idea that many unsupervised methods do that. And if you, another analogy is that it's similar to piecewise SP-line regression. What is piecewise SP-line regression? It says, do you remember we have in linear regression, we want to, what do we do in linear regression? Soon we have some data points, we fit a line to that, right? However, what if the data is not linear, the pattern of data is not linear, such as this? Okay, if we apply linear regression, it would be very bad. It should be something like this, right? So it's not good. Therefore, we can approach it piecewise. In each piece, we apply a linear regression on this, and then in the second piece, we apply a linear regression again. Then in this way, we can have kind of several linear regression algorithms on pieces of data. Then we can also regress nonlinear patterns of data. This is the algorithm, an algorithm called SP-line regression. SP-line regression. You can take a look at reference 9. So LLE has a similar approach, but for dimensionality reduction. What does it do? It says it unfolds the nonlinear manifold by locally unfolding the manifold piece by piece. And what do I mean? Assume this is a nonlinear manifold, right? And what do? I consider it piecewise. I divide it into several pieces, right? And then I put this piece here, then the second piece here, and the third piece here. Then, as you see, although it was curvy, but I could unfold it by treating it piecewise. So this is the ideal local linear embedding. It treats the manifold piecewise or locally. So it was proposed in reference 1 and developed in references 10 and 6. So one is the Journal of Science, and one of these is the Journal of Machine Learning Research. It has 3 steps. Okay, so its steps are these. First, it finds k-nearest neighbors graph of all training points. So k is a hyperparameter here. You calculate a k-nearest neighbor graph for seeing. So if 2 points are close to each other in the input space, they should be connected in the KNN graph, right? Then what does it do? It tries to find the weights of reconstructing every point by its neighbors. What do I mean? Assume I've formed a k-nearest neighbor graph, and then for xi, assume my k is 3, right? So these are the 3 nearest neighbors, and I denote them by xi1, xi2, and xi3, right? Okay, so let me clean it. And so I can do it for every point, right? Now, I say, what if I don't have xi? I want to represent xi as a linear combination of its neighbors. So xi here, I can find that it can be represented, it equals to here, wi1 xi1 plus wi2 xi2 plus wi3 xi3, right? It's a linear combination of its neighbors, and the coefficients of this linear combination are called wij. Then what do I do? The idea is this. So here, for example, we are in multiple dimensions of input space. Assume, for example, this is R4. We are in 4 dimensions, right? Now, in the low dimensional embedding space, here it is R2, for example. Let's put the points, the embedding of the points, in a way that also the corresponding embedding points are reconstructed by the embeddings of their neighbors. So what do I mean? Here, xi is mapped to this point. xi1 is mapped to, for example, y2. xi2 mapped to y3. xi4 mapped to y9, doesn't matter. Or xi3 mapped to y7. So I mean, these are the embeddings of that x's, okay? Now I use the same weights. It's wi1, so this is wi1. wi2 for, so y3 is the embedding of xi2. That here I have wi3, here it is, wi3. Also wi4, here it is, wi4. So I use the same weights in order to reconstruct the embeddings by the linear combination of its embedded neighbors using the same found weights. So the idea is simple. The idea is simple. We see how every point in the input space is reconstructed, is represented by its neighbors. I use the same weights for representing the embedded points in the low dimensional space. But we need to now model it mathematically. So the idea is simple. Let's model it mathematically. So first off, as we said, the first step, k-nearest neighbors. Let's talk about it. So a KNN graph is formed using what? Pairwise Euclidean distance between the data points, right? So I have several data points. I can find the pairwise Euclidean distance between each point. Then every data point has k neighbors. So I can sort the distances of points. For every point, I can sort the distances to all other points in ascending order. And then I can take the k first ones. It gives me the k nearest neighbors, right? Okay. Let xij be the jth neighbor of xi. And the points, let them be d-dimensional. And I put the so I put the neighbors of xi in column wise in a matrix. So, and I denote it by capital Xi. So capital Xi is a matrix whose columns are the neighbors of xi, right? And therefore it will be d by k dimensional, right? Because each neighbor is d dimensional and we have k of them. Okay. It includes the k neighbors of xi. Then what do? We assume that k is large enough so that k-NN graph is connected. We assume that, because if k is small, then we might have a disjointed graph. But as we assume that k is large enough, so it is connected. Now we go to the second step of local linear embedding, and that's linear reconstruction by the neighbors. Okay, what was that? So do you remember we said, in this step, we want to find the weights for reconstructing every point as a linear combination of its neighbors in the input space, Okay, so let's do that. We want to model it mathematically. How? We say x for every point xi, I want it to be represented as a linear combination of its neighbors. Xij is the jth neighbor of xi, right? And this wij tilde is my optimization variable, my linear the coefficient of linear combination, right? And also I want this distance between these two to be minimized. I want the distance between every point by its linear combination of its neighbors to be minimized. Therefore, I minimize the L squared L2 norm, which is a squared Euclidean distance, right? And also I have summation. Why? Because I have n points. So I want to minimize this distance while I want the summation of the weights to be 1, because I want every point to be a linear combination of its neighbors. Let the weights be sum to 1. Okay, for all I from 1 to n, right? So now, and what is this capital W tilde? That has all of the wij tildes in it, and it is a matrix. Why? Because for every point xi, I have k weights, right? If I put the k weights in a vector, I can denote it by wi tilde vector, which is k dimensional because I have k weights. Okay, and if you put them, let me think. If you put them row wise, the wi tildes row wise, right? You will have a matrix w tilde, which is n by k. Why? I have n data points, each of which has k weights for linear reconstruction by its neighbors. Okay. So what were we saying? Okay. So this is the optimization problem. As we say, I have seen always, all of the machine learning is optimization. So we modeled what we had the idea using optimization as an optimization problem. Now let's solve it. So the constraint also, as I said, means that the weights of linear reconstruction sum to 1 for every point, right? Okay. But there is a problem. Can you tell me, without reading this paragraph, can you tell me what is a problem and issue with this constraint? Summation of wij tilde equals 1. And wij tilde is the optimization variable, right? There is a big issue with it. Assume I have 3 weights. Assume k is 3. Then one of the wij's is 1, for example. One of them is 1,000. One of them is minus 1,000. The 1,000 and minus 1,000 cancel each other, and the other one becomes 1. So Some weights might be very negative, large negative numbers. Some weights might be large positive numbers. They cancel each other. They still sum to 1. So we'll have explosion, and we'll have overflow in computer, overflow of the optimization variable. We have explosion. What didn't the authors of this paper think about it? Of course, they thought. One of them was Sam Royce. I think we can call him the god of manifold learning. So he knew what he was doing. But why? The reason that this problem doesn't happen is that we will solve this optimization problem. We will find a closed form solution. Okay. If we couldn't find a closed form solution and we had to solve it iteratively, such as using interior point method or Newton's method or gradient descent, whatever, it would explode gradually. You would see it in your computer that it is getting larger and larger. But as we find a closed form solution, this doesn't happen. How did I know that? I didn't notice that this constraint has this big problem. How did I find out? I developed a new algorithm inspired by LLE for images using structural similarity index, or SSIM. If you don't know what SSIM is, search it. SSIM is just for the idea of SSIM is that it says mean squared error is not a good measure of difference of images for visual eye. For our visual system, they found another way of measuring the difference of images, and they called it a structural similarity index, or SSIM. It says how visually different the two images are, especially for visual system of human. Okay, so I said, as you see, mean squared error, MSE, is used in the loss function of LLE. Let me replace it with the SSIM distance. I did that. I coded that. I was happy. I solved the optimization problem. I solved it iteratively using alternating direction method of multipliers, ADMM. I solved that in its steps. I used gradient descent, and I found out, oh, why is the weight gradually exploding? And then I thought about it and found out, oh, there is a problem with the constraint in this. So in that algorithm, I changed the constraint. What did I put as the constraint? Can you tell me? Put yourself in my shoes. You are Benjamin several years ago, assume. Okay, you were a PhD student. You were designing an algorithm. You faced this problem, and this constraint, the weights were exploding. What would you do? Not in order to resolve this problem. Yeah, give me some ideas. How would you change this constraint? One option is this. I said, let me have the second norm of WI. So as you see, WI has all of the WIJs in it. The L2 norm be 1. Then this doesn't allow. Then this doesn't allow what? The explosion of weights. Because the length of W now, the length of W is constraint to be 1. And we can't have very large negative numbers or very large positive numbers. I changed the constraint and it worked. Okay. So now let's solve this optimization problem. Optimization problem 1. By the way, this is not equal to that. I changed that in my algorithm. Okay, we can restate the objective. This is the objective function that we had. Okay, let's restate it in matrix form. So this, I can write it in matrix form, and it becomes xi w I tilde, right? Then what happens? Also, this constraint that I had, let's write it in vector form. So I can write it as vector 1 transpose wi tilde equals 1, right? Because this simply means add all of the elements of wi tilde. Then also, do you agree that if I multiply the the sides of this left multiplied by xi, I will get this. I'm gonna use this also. Xi equals xi 1 transpose wi tilde y, because the 1 transpose wi tilde equals 1. Now I'm gonna simplify this cost function. So I have this. Okay, what do we do here? I replace xi by xi 1 transpose wi tilde, right? Interestingly, I have wi tilde here and here. Let me factor it out, right? Now this is a squared L2 norm, so I can write everything. Something, a squared L2 norm is equal to something transpose something, right? So I can write it that this transpose this. And we know that transpose changes the order, right? Then what do we have? Now I define this, which has appeared in the middle, I denote it to be gi, which is k by k. Why? Because this is, I think, d by k. This is k by d. So this is k by k. Gi, why do I call it gi? It stands for gram matrix. Why do I call it gram matrix? Do you remember? I said kernel also is called gram matrix. In kernel SVM, I said that. Okay. And it's very similar to kernel. This is linear kernel, right? Now replace x with what you have here. So it's kind of a kernel between xi, transpose minus xi and xi and itself, right? Okay, so I simplified the cost to be this. Also, I wrote the constraint in the vector form or matrix form. And now these are my optimization variables. Okay, so let's solve it. How? What do we do usually? Form the Lagrangian, take derivative, set it to 0. Okay, so this is the Lagrangian, and this is the Lagrange multiplier or dual variable. Take derivative with respect to optimization variable, which is wi tilde for every I, right? If you take derivative of this with respect to wi tilde, what do you get? This is quadratic with respect to wi tilde, right? Therefore, it becomes 2gi wi tilde. But where does the summation go? It goes away. Why? Because it's the derivative is with respect to wi tilde for a specific I. For a specific I. Do you remember? So as I said before, so this is w1 tilde g1 w1 plus until w n tilde gn wn. Now assume I'm taking derivative of L Lagrangian with respect to w 1 tilde, for example. All of other terms are constant with respect to w1 tilde, so they go away and I only have this. That's the reason that the summation goes away. And also here, this is linear with respect to wi tilde, so we'll have a lambda I w lambda I1, and again for the same reason summation goes away. Set it to 0, rearrange the things. So if you set it to 0 and rearrange, you'll have gi here, which is a pain in the neck. Left multiply the size by gi inverse, then you will get this. Okay, which I rearrange it to be this. Lambda I is a scalar, so I can move it back and forth in the multiplication. If you take derivative with respect to Lagrange multiplier, what do you get? You always get back the constraint, right? And this is the constraint that we had. Okay, now using equations 5 and 6. So we know that this is wi tilde, and we know that this 1 transpose wi tilde should equal to 1. So I put this 5 in equation 6. I will get this. Rearrange the things. You will get this. By the way, we know that 1 transpose gi inverse 1 is a scalar. Is a scalar, right? Therefore, I'm allowed to bring it to the denominator. Okay, now I put this equation 7 back in equation 5. As you see, we are using the method of Lagrange multiplier. Okay, then what do we have? We'll get this. Interesting. It gives us a closed form solution. What did we want to find? wi tilde. and it exactly gave us a closed form solution. Interesting. So now let's talk about GI. Do you remember this is what we defined as GI, gram matrix, which was K by K? It's K by K, its rank is at most minimum of K and D. Why? Because this is D by K, this is K by D. As a result, according to linear algebra, the rank of GI is minimum of K and D. Okay. Now, if D is less than K, what do I mean? D is the dimensionality of data. K is the number of neighbors. If D is less than K, then GI is singular. Why? Because GI is K by K. If D is less than K, it means that its rank is D. Its rank is D. Why? It is K by K. So it's not full rank. So it's singular. And however, we have GI inverse in the solution. It's a problem. It shouldn't be singular, right? So if that happens, therefore, we have several options. Either we increase, we decrease K, so K becomes less than D, or what happens? We just strengthen the main diagonal of GI. It was the hack which we use a lot, especially in Fisher discriminant analysis and many other parts in machine learning. Do you remember? So we have GI plus epsilon I, where epsilon is a small positive number. Usually data are high dimensional, such as images. So this doesn't happen usually. Usually D is large, so K is much less than D. Okay. Strengthening the main diagonal of G is referred to as regularization in LLE. You can see it as a regularization, right? Okay. Now we go to the third step of LLE. So the second step of LLE is also over. Now the third step of LLE. What do we do? So we found the weights for linear reconstruction of the points in the input space. Now we use the same weights for embedding in the embedded space, in the low dimensional embedding space. So we found the weights for linear reconstruction in the high dimensional input space. Now in the third step, we embed data in the low dimensional embedding space using the same weights as in the input space. Okay, so this was the idea. Let's model it mathematically. How? We say yi is the embedding for xi. Okay, and this is yj. Also I have wij. So what is this wij? The same weight as we had in this second step. However, in the second step, we had tilde. Here we don't have tilde. I will tell you why. Okay. But I'm using the same weights. Okay. And so yi, now this is a linear combination of its neighbors, the embedding of the neighbors. And I wanted the squared Euclidean distance between them to be minimized. And sum over all of the points. Right, and my optimization variable is the y, is the embedded points. Now I define two constraints. One of them, let the mean of the embedding be 0. Okay, so no matter if the mean of the input, the data set in the input space is 0 or not, in the embedding space, after I embed them, I want the embedded to be around 0 origin. I want the mean to be 0. Okay. Also, I want this to be I. What do I mean by this? So it's equal to yi minus mu. Assume mu y. Mu y. I mean this is mu y. The mean of embedding. Okay. Times yi minus mu y tilde. What the transpose? Why? Why am I allowed to write this as this? Because mu y is 0, right? And what is this? This is a covariance matrix in the embedding space. I want it to be I. So these two together means that I want the mean of embedding to be 0 and the covariance to be identity. And what do I mean by covariance to be identity? It means that it will be like a hypersphere in the embedded space. If it is 2D, it should be similar to sphere, to a ball. Okay, so that's the thing. Now, here I put the embedded points. Let me put the embedded data points y1 to yn row wise. Why do I put it row wise rather than column wise? Because it makes it easier for us to calculate. Okay, that's the reason. So let's put them row wise, and it gives us n by p matrix, because I have n data points, each of which has p-dimensional embedded points. Yi is p-dimensional, is the ith embedded data point. Wij, now this is the relation of Wij and Wij tilde, which I found in the second step. So I define Wij to be Wij tilde if xj is in one of the k-nearest neighbors of xi, otherwise 0. Why do I do that? I want you to understand the difference of Wij tilde and Wij. This is the reason. Because do you remember, in the second step, when I put Wij tildes next to each other in a vector, it became a k-dimensional vector. Let's see. Do you remember this? This Wi tilde, it had Wij tildes as a vector. It is k-dimensional. So I only put the W's of the k-nearest neighbors, right? Now in the embedded space, in the formulation, it is easier to define an n-dimensional W, which is 0 in all other elements except the neighbors. And in the for the neighbors, it has Wi tilde. So what do I mean? Assume Wi tilde is let me think. Assume it is 1, 2, half transpose. Assume k is 3. Okay. Then Wi, what happens? Assume n is 5. And assume for the ith point, the neighbors are xi1. So xi1 is actually x2, assume. But yeah, doesn't matter. xi2 is x3 and xi3 is x5. Assume, okay? So the neighbors of xi are x2, x3, and x5. Then what happens? My Wi becomes this. So it gives me 0 because x1 is not one of the neighbors, right? Then x2, its weight is 1. X3 is also actually xi2, its weight is 2. X3 is not among the neighbors. X4 is not among the neighbors, 0. X5 is the third neighbor whose weight is half. So this is what I mean. This is the difference of Wi and Wi tilde. Okay. Wi is 5-dimensional because n is 5. So here, as we said, I just explained this formula. Now, if I put the Wij's in a vector form, it becomes n-dimensional rather than k-dimensional, right? Okay. What did we have here? Yes, okay. Now let's write the cost function in a matrix form or vector form. How can we do that? So if I define vector 1i, which is an n-dimensional vector whose ith element is 1 and all other elements are 0. Okay. Then I can write this in this form. I can say y transpose 1i, y, because this filters the ith row of the matrix y. Therefore, it gives me yi. And also, I can write this as y transpose wi. I can write this in matrix form. Okay. We have this. Then this summation, I can absorb it into the norm to make it in matrix form. So this is vector form, wi. Let's make it matrix form. absorb the summation in, then it gives me W transpose, where W is the matrix, right? And the Euclidean norm, the L2 norm, became Frobenius norm. Okay, I wrote it in matrix form. Then we know that Y transpose appears, so I can left factor out Y transpose, right? We have this, and we know that I transpose equals I, because I is symmetric. Then let's simplify this. I know that everything, something Frobenius norm squared equals trace of that thing transpose that thing. So I have trace of this thing transpose this thing. So this thing, and if I transpose it, it changes the order also. This thing, transpose this. Okay. Then what? One I, I wrote it in, I absorbed the summation inside Y to make it matrix form. So one I became identity, and Wi became W matrix, W transpose matrix. Note that why is one I became identity? Because we know identity is a diagonal matrix. So its off diagonal elements are 0. Therefore, it makes sense it's one I, right? Okay. So we had this. Now we were here. So now I use the cyclic property of trace. So it gives me this and these, right? Now I can name this, which has appeared in the middle. I name it to be M, matrix M. It is N by N. Why? What was W? I think W was, I don't remember, I should see. W, yeah, W is N by N. So this is N by N, this is N by N. Therefore, matrix M is N by N. Okay. Interestingly, equation 13 is very interesting. Why? My identity minus W is a Laplacian matrix, Laplacian of matrix W. Why? What is Laplacian? Let me tell you something here. Assume I have some matrix X, doesn't matter. Okay. Yes. According to linear algebra, Laplacian of this X equals matrix D minus X. Yeah, I think I'm right. And what is matrix D? Matrix D, if you sum the rows of X, it gives you some scalars, right? Now put these scalars as a diagonal of a diagonal matrix. So I put it here, I put it here, I put it here, put it here. The other elements are 0. This is matrix D, okay? And it's called degree matrix. Okay? D minus X is called Laplacian matrix of X. Why? Because you can see X as a graph. You can see every matrix as a graph. Okay? And Laplacian of this graph is D minus X. Okay? This X can be represented as an adjacency matrix of a graph. Okay? So this is Laplacian, and it is related to linear algebra as well as graph theory. Okay? Graph theory. Now, interestingly, what we found, what is this? I minus W. It's a Laplacian of matrix W. Why? Let's see. Let's see. So W is some matrix, right? What are its rows? So as you see, its rows, its transpose, right? Its rows as W1 to Wn. So what do I mean? Here, this is W1. Here, this is W2 until Wn, right? W1 are all of the weights for the first point. Many of its elements are 0. K of its elements are not 0 and are equal to W1 J tilde, right? As I said, W1 is N. This is an 1 by N, right? This is 1 by N. K of its elements are not, the weights which we found in the second step, and all the other elements are 0. Now let's find the diagonal, the degree matrix of W. What is the summation of W1? Can you tell me, please? If you tell me, I will dance. It means that you have understood it. What is the summation of W1? Many of its elements are 0, except K of it, the K elements. What is the summation of those Wij tilde? Let's go back to the second step. In the second step, what was the constraint? What was the constraint? Equation 1. 1. Did you understand? So according to this constraint, we know that the K Wij tildes are 1, their summation is 1, the rest is 0 in Wij, right? So every row of W, matrix W, sums to 1. Interesting. Do you see how things are connected to each other in this algorithm? Sam Royce was a genius. So this becomes 1, this becomes 1. All of them becomes 1 and the rest are 0. And what is this? Identity matrix. Now what is Laplacian of W? It is D minus W, which is I minus W. Interesting. What we found here is the Laplacian matrix of W. So M is related to the Laplacian matrix, right? You can see that the quadratic Laplacian matrix. And I have a question. According to linear algebra, I think I have said it here. Did I say it? I have said it somewhere in the slides. According to the linear algebra, if the, as I said here, W or X here is, you can see that the adjacency matrix of a graph in graph theory, okay? In graph theory, there is a lemma, okay? There is a lemma saying that if my graph has K parts, K disjointed parts, let me change the name, F disjointed parts. I don't want the K to be confused with the K in K nearest neighbor. What happens? If you form its Laplacian matrix, okay, then you find its eigenvalues and eigenvectors of the Laplacian matrix, okay. You will see that, as far as I remember. Just give me a second. One K part, one part. Yes, you will find K of the eigenvalues are 0, and their corresponding eigenvectors are vectors 1. Can you believe that? This is a lemma in games in graph theory. Okay. So when you have K disjointed parts, the Laplacian, if you apply eigenvalue problem on Laplacian, I said K, F. If you have F disjointed parts, F eigenvalues become 0, and F eigenvectors become vector 1. Now, do recall what I said in the step 1 of LLE. I said, we assume that the graph of, we have chosen K in a way that the graph of data is connected. Here I said that, is connected. Therefore, how many parts does the graph have? Does the graph of W have? When it is connected, how many parts is it? Please tell me. I have a connected graph. How many parts does this graph have? One part, right? If I use this lemma, it means that how many eigenvalues are 0? Therefore, for W, in our case, I have 1 0 eigenvalue and 1 eigenvector, corresponding eigenvector, which is the vector 1. Okay, so that's one thing which we should note. Okay. So let's see what we found. So we simplified the cost function in the third step. It became trace of y transpose my. Here it is. Also, I write the constraints that I had in matrix form. So 1 over n, y transpose y equals I, identity, the matrix, and y transpose 1 equals 0, right? I wrote it in matrix form. Now, let's solve it. What do we do? Lagrangian, take derivative, set it to 0. This is the Lagrangian, and lambda here is the eigenvalues, okay? Then take derivative with respect to y, which is the primal optimization variable. Then what does it give you? It gives you 2my, because this is quadratic with respect to y. And also this is quadratic with respect to y. So it gives you 2y lambda over n. Set it to 0. These two 2's cancel each other, right? And you will get this. What is this? Recall preliminaries. What is this? This is an eigenvalue problem for matrix M, where 1 over n lambda are the eigenvalues, right? Okay, and according to just the lemma in game theory, in graph theory, which I said, what this is, so y are the eigenvectors of matrix M, right? And we saw that matrix M is related to the Laplacian of W. And we saw that the graph of data, we assumed that we chose K, so the graph of data is connected. Therefore, according to graph theory, I have one zero eigenvector, zero eigenvalue, and its corresponding eigenvector is 1. Okay, therefore I should ignore that. I should ignore that zero eigenvalue. Y are the eigenvectors. I should sort them from smallest to largest eigenvalues. Why? Because this is a minimization problem. Recall preliminaries. I should sort them. And I should ignore the first one. Why? According to graph theory. Because this one is always 1, and whose eigenvalues are 0. So I ignore the first one. This is the lemma that I talked already about. This slide I already talked about. Okay. So we found the solution interesting. The solution of LLE, the third step, is also closed form. If you see the power method for solving the eigenvalue problem as a closed form solution, okay? If you see it as a black box, then it's also a closed form solution. Interesting. It was a breakthrough in the year 2000. Okay. Let's see some examples of LLE embedding. Swiss roll. So this is Swiss roll. You see it a lot in the restaurants, right? Then we can, this is highly nonlinear, right? Highly nonlinear. In M, this is in 3D, right? Now, if we apply LLE to it, it unfolds the manifold to become 2D, right? And P here is 2, D here is 3, right? Interesting. It can completely unfold it, right? And as I said in the first slide, it's like that it has unfolded locally, piecewise. Also, on the Frey facial dataset. Frey facial dataset is a dataset of faces that is one person who has different emotions and different facial poses or facial expressions on his face. So if we apply LLE on this, of course, for example, here where it is smiling, all of its neighbor points are almost smiling, right? If, for example, here his mouth is a bit open, so these points are also, his mouth is open. Here, he's putting his tongue out. Therefore, this neighbor also is putting his tongue out. right? Here, he's closing his eyes. The neighbors also are almost closing their eyes. Interesting. So it has found the semantic relation of the data points. And another interesting thing, if you see where it is embedded in 2D, it is 0. This is 0. Why? Because our constraint in the third step, I want the mean of embedding to be 0. Again, here also, if you see it, this is 0, this is 0. Almost, right? So the mean of the embedding is 0. And interestingly, you can see that these are almost equal. Why? Because I wanted the covariance to be identity. Right? Very interesting. Acknowledgement, some slides are based on our tutorial paper, Local Linear Embedding and its Variance, Tutorial and Survey. It's also a chapter in our book. You can, Elements of Dimensionality Reduction and Manifold Learning. Some slides of this slide deck are also inspired by the teachings of Professor Ali Qudsi at the University of Waterloo. I have coded LLE, and you can find it in my GitHub. This is the, so I have coded generative LLE, which is my proposed algorithm, and also LLE in it. You can take a look at that. Also LLE, you can find it in scikit-learn, the scalar. Here. Okay, these are the references. So this was the paper, which was paper of LLE, nonlinear dimensionality reduction by local linear embedding by Sam Royce and Saul, in year 2000. Also, they explained their method more in this paper. Think globally, fits locally, which is the main idea of unsupervised manifold learning. Unsupervised learning of nonlinear manifolds. Also here. So they have published it in Journal of Machine Learning Research in the year 2003. Also, these are their other references. Okay, let's go to the next lecture. So with we talked about most of the important spectral dimensionality reduction algorithm, right? Now let's change a bit of gear and go to variational inference and factor analysis and probabilistic PCA, which are probabilistic dimensionality reduction algorithms. Okay. So variational inference. Consider a data set x1 to xn, okay? And each of which is d-dimensional, right? Assume that every data point xi is generated from a latent variable zi, which is p-dimensional. This is a very important thing. Also in causal inference, in very different aspects of probabilistic machine learning, you see this. When you have some data, you have some variable, it probably has been generated from another variable, let it be zi, and their dimensionality might differ. This might be p-dimensional, but this is d-dimensional, right? For example, if I have a headache, the reason might be something latent. Maybe I got angry, right? So everything in this world has some latent factor, okay? And we can call it latent variable or latent factor, which is usually hidden. We can't see it. We see this. This is observed variable. Just one interesting thing in parentheses. You know Professor Ali Qudsi, right? Okay. In Clubhouse, he had a talk, but it is in Persian, unfortunately. So if you don't know Persian, you might not understand it. So he had a talk and he explained miracles and let me think, and metaphysics, right? Yes. No, not metaphysics, supernaturals, because there is a difference between metaphysics and supernatural in philosophy. Some people confuse this. He talked about supernatural and miracles, and he tried to explain them as a probabilistic graphical model like this. Okay, just for the people who know Persian, you can look at this title, Pascal and Asai Musa. It means that Pascal and Moses, what is a stick, right? Just an interesting thing that he had a mathematical approach to a supernatural thing. Okay, Professor Legosi has done that. You can take a look at it, and that's interesting. Anyway, so everything in this one, you can see that it has a latent factor. Okay, so now let's write the base rule for this probabilistic graphical model. P of Zi given Xi equals P of Xi given Zi times P of Zi over P of Xi, right? Okay. This P of Zi, let it be an arbitrary distribution, and I call it QZ. So that's the prior of the latent factor, right? Suppose the parameter of conditional distribution of Zi on Xi, I mean this, be theta, because every distribution has some parameters, right? For example, Gaussian distribution has mean and covariance. Hence, I can write it in this way. Okay, I can write it in this way. I add theta as a variable. So now I change the base rule to be this. I can say P of Zi given Xi and theta equals P of Xi given Zi and theta times P of Zi given theta over P of Xi given theta. I think it's obvious, right? Because if you multiply this by this, what does it give you? It gives you P of Zi, P of, give me a second to think. Yes, I think I'm right. What does this give you? I think I made a mistake here. Just give me a sec. Yes, and these two are equal. P of Xi over Zi given theta, right? Okay. Now, consider the KL divergence or Kullback-Leibler divergence between the prior probability of latent variable, which was Q of Zi, and the posterior of the latent variable, which is P of Zi given Xi and theta. What is KL divergence? Assume I want to see the difference of two distributions. There are several ways to do that. One of them is KL divergence. When two distributions are exactly equal to each other, the KL divergence is 0. When they are not equal to each other, the KL divergence is greater than 0, right? So let's consider the KL divergence as, according to the definition of KL divergence, this KL divergence is this. By the way, it's not symmetric, okay? So it's integral of QZI, logarithm of QZI over this probability here, DZI, okay? Now I can write, I know that logarithm of A over B equals logarithm of A minus logarithm of B. So I can simplify it in this way. Then what happens? According to equation 2, what was equation 2? This was equation 2, right? The base rule. So I can write, I'm replacing this P of Zi given Xi and theta by the base rule that I had. So I have this term and the numerator and the denominator. So I have 3 terms, right? Afterwards, what do we have? We know that P of logarithm of P of Xi given theta, which is this. This term is not dependent on the variable of integral Zi. Therefore, I can bring it out, right? And so it will become logarithm of P of Xi given theta, integral of dZi, which becomes 1, So times 1, right? So I have this plus the rest in the integral. Okay. Then I can simplify this back to using this formula, back to what I have here. Okay. Then what happens? The denominator, I can simplify it to become P of xi and zi given theta, right? According to the conditional probability that we had. Then, interestingly, this is the KL divergence by definition. This is the KL divergence between QZI and the P of xi and zi given theta. Okay, so I could write this KL divergence and I simplified it in this way. Okay, now let's rearrange this. So this is the left-hand side equals the right-hand side. Okay, rearrange the terms, you will get equation 3. Okay, guys, please notice this is an important lecture. Did you understand what I did so far? Yeah, so I simplified the KL divergence between prior of Zi and posterior of Zi. I found this and then I rearranged this. I got this. Okay. I want to find one of the most important formulas in machine learning. So this is what I had. Now I define evidence lower bound, also called ELBO. This is a very important formula in machine learning. Evidence lower bound or ELBO. And what is it? I defined it in this way. L of Q and theta equals minus KL divergence between QZI, prior of ZI, and probably conditional joint probability of XI and ZI given theta. Okay. So so basically here I defined it to be what? To be L of Q and theta. By the way, this L is not Lagrangian. Don't confuse it. That's ELBO. Okay. Then I rearrange things. So I bring this to the other side. It gives me this. Okay. No. So sorry, I didn't rearrange. I apologize. Note that minus here. Note that minus here is in the definition of ELBO. So the whole thing is ELBO. I didn't rearrange it, so I have this. And then now I rearrange it. Now I bring this to the other side. I will get this. Okay. So ELBO, which I defined it here, can be restated as this. We know that this is one of the properties of KL divergence. It is non-negative. It is either 0 or positive, right? So this term is non-negative. Therefore, we have this minus 0 or something greater than 0. What does it mean? This is less than or equal to this term, right? What does it mean? This part, which we called it ELBO, is a lower bound for the log probability of xi given theta. Hence the name evidence lower bound. Why do we call it lower bound? For this reason. Also, P of xi given theta is also called evidence. Okay. This lower bound gets tight when, what do I mean by getting tight? Because this is a lower bound also. This is also a lower bound. But this is a better lower bound, right? So it gets tight when, what happens? When this is almost equal to the right-hand side, almost equal to this, right? When does this happen? When does this happen? According to this equation 5, when these two are almost equal to each other, the KL divergence is almost 0, right? And we know that it's also greater than or equal to 0. Therefore, it's sandwiched between 0 and 0. Therefore, it must be 0. And we know that then when the KL divergence of two distributions is 0, they are equal to each other. Therefore, this equals this. Q of Zi equals P of Zi given xi and theta. Okay. So what do we have? Yeah, this is what we had found. This is the repetition of one of the formulas here. Okay. Then let's visualize it. Okay, I think Bishop's book has this visualization. Okay, so what does it do? It says that assume this is elbow, this line is elbow, right? And this is elbow, right? This is 0, so this is the amount of elbow, right? Also, this part is this scale divergence. We know that their summation should become this logarithm. This, right? Now, what do we want to do? We want to increase this. Or in other words, we want to decrease this. So we want to increase this part or decrease this part. So elbow gets closer to the log loop. Okay, gets tighter, right? As I said here, when does it get tight? When QZI equals P of ZI given Xi and theta. Let's see. According to maximum likelihood estimation, we want to maximize the log likelihood of data, right? And also, so this is maximum likelihood estimation, right? We want to maximize the likelihood of data. Also, we know that this elbow is the lower bound. We found it. So maximizing the elbow will also maximize the log likelihood. This is a good technique in optimization. I have talked about it in my optimization course. Assume in your optimization problem, you have something you want to maximize it. It's very hard for you. You can't maximize it. You find a lower bound for it and you maximize the lower bound. By maximizing the lower bound, the function also needs to be maximized. Or if it is minimization, sorry, yeah, I think that's correct. I have a maximization problem. I found some function. It's hard. I maximize. Likewise, if I want to minimize something, it's hard. I can find an upper bound on it, and I minimize the upper bound. So I can do it both ways. Here, I want to maximize the log likelihood. Therefore, let me maximize its lower bound, elbow. Okay. Now, we know that equation 6, which is this, holds for any prior distribution Q, right? Any prior. Did I make any assumption on the distribution of the latent factor? No, it was Q. Okay, we want to find the best distribution to maximize the lower bound. This is exactly what we want to do. What distribution gives me the tightest lower bound? Okay. No, if elbow is maximized. This is elbow. When elbow gets close to its upper bound, it's tight, right? So let's do expectation maximization, right? Let's see. So this is our elbow. We want to maximize it, right? So we maximize it, and our optimization variable is Q. Let's find the Q. This is the E step. Then we maximize the elbow again, but I replace Q with with QT in the Tth iteration, and it gives me theta. So I wanted to do maximum likelihood estimation on elbow, Q, and theta. However, so it is theta, my optimization variable, right? However, I have unseen data, unobserved data, and that's Q. Therefore, I can't do MLE. I need to do expectation maximization. Recall expectation maximization in the sessional mixture distribution. I already talked about it. Okay. So therefore, we have to do E step and M step. In E step, I found Q. I replaced Q with what I found, and I found in M step, I found theta. I do it iteratively. It is an alternative optimization until convergence. T denotes the iteration index, right? And this is expectation maximization for variational invariance. What we are talking about is called variational invariance. Okay, now let's go deep into E step and M step. Okay, in E step, what do we have? Maximize the elbow with respect to Q. According to equation 5, what was equation 5? This was equation 5. L of Q and theta is logarithm of P of xi given theta and minus KL this, right? So I'm replacing this elbow with logarithm of this minus KL. This is, I just put equation 5 rather than the elbow. Okay. Then what happens? So I'm repeating the first term. The second term, I have maximization of minus something. It's equivalent to minimization of that thing, right? So I'm minimizing this KL divergence. Okay. The second term is always non-negative. Do you agree? Because KL divergence is either 0 or positive. Always non-negative. Hence, its minimum is 0. The best case, KL becomes 0. So set it to 0 for this minimization. It gives you this. So QZI equals P of ZI given XI and theta, the previous theta. Okay, which was already found. We already had found it for making the lower bound tight, right? Okay, so the solution of E step is this. Replace Q of ZI with P of ZI given XI and theta, the previous theta. Let's see it in the visualization. What do we mean? It pushes the middle line toward the above. So pushes this above to make the lower bound tight by maximizing the elbow, right? We want to maximize the elbow. Okay, now let's go to M step in the expectation maximization in variational invariance. So we have maximize the elbow with respect to theta now. Okay, according to equation 4, what was equation 4? Definition of elbow. Definition of elbow. Okay. So I have this, maximize this. Then I use the definition of KL divergence. So I replace this KL divergence with this definition. I will get this. Okay. Now I use the formula of logarithm of A over B equals logarithm of A minus logarithm of B, right? So it gives me these terms. Okay. Now this second term here is constant with respect to theta. We are maximizing it with respect to theta, but this is constant. So its derivative becomes 0. And I don't need to optimize it because it's constant, right? Therefore, so this is therefore I can drop it. Why? For finding theta, see, I don't need the maximum cost function. I need the optimization variable which maximizes that. Therefore, I can drop the constant term in the cost. So I can drop it, right? So I maximize the first term only, which has theta in it. Theta in it, right? Okay. What is this is interestingly the definition of expectation. Recall preliminaries. So I can replace it with the definition of expectation with the probability Q. Here, this is the probability, this is the function, right? This is expectation. The function, and this is the probability. Okay. Now, so we just found that the M step gives us this. Argmax of expectation of logarithm of P of xi and zi given theta for a probability of Q zi. This is what we found for M step. Okay, so what does this M step do? It pushes the above line higher. So it pushes this higher. So it's making a game. It's playing a game. Once it's in E step, it pushes elbow above. Elbow wants to reach to the log likelihood. The M step says, not so soon. it pushes the log likelihood above. Then each step again, ELBO goes up, then the log likelihood goes up. Then ELBO goes up, then the log until ELBO gets very close to the log likelihood. Right? Interesting. So they are playing a game. To summarize, the EM, expectation maximization in variational inference, is this. Equation 12 is E step, equation 13 is M step. Sometimes the parameter theta is absorbed into the latent variable Zi. You can do that, okay? Sometimes in the literature they do that. And so according to the chain rule, this is chain rule in probability, right? So I can write this joint distribution as P of xi given Zi and theta times P of Zi given theta times P of theta. Okay. Now consider this as one probability term. So you can write it as P of Zi. We have absorbed theta into Zi, therefore it becomes this. Sometimes in the literature you will see this. Okay. Now we talked about variational inference. Okay. Let's talk about factor analysis, one of the probabilistic dimensionality reduction algorithms. So factor analysis is one of the simplest and most fundamental generative models. What do I mean by generative? Generates the probabilistic graphical model, which I showed to you, which has a latent variable. This is a generative model. It generates xi. Here you can see it. Zi generates xi, right? And factor analysis is a very old method. It is one of the most fundamental algorithms as generative model. So factor analysis assumes that every data point xi is generated from a latent variable Zi. The latent variable is also referred to as the latent factor. Hence the name factor analysis. Why do we call it factor analysis? Because of latent factor. Okay. In factor analysis, we assume that the data point xi is obtained through the following steps. Okay. So first, linear projection of the p-dimensional Zi onto a d-dimensional space by projection matrix lambda. Right? And lambda is d by p. You know, linear projection, we have seen it a lot in this course, right? So by linear projection of Zi, we get something, then we add some linear translation. And then we add some Gaussian noise epsilon, which is epsilon is also a vector of noise with some covariance matrix, d by d. As it is a vector, it's called, it doesn't have variance, it has a covariance matrix, right? Which is d by d. Its covariance matrix are denoted by psi. Okay. So what I said is this, I think. Yeah, here it is. So lambda Zi projects Zi into some subspace. Then we add some mu, some translation, some mean. Then we assume this is the mean of some Gaussian distribution with covariance psi. Right? This is the mathematical modeling of what I said here. What I said here. Okay. As noises in different dimensions are independent, do I care what noise I apply to which dimension? No, I don't. They are independent. The covariance matrix is diagonal matrix. Okay. And probabilistic, it can be seen as a graphical model, probabilistic graphical model in this way. So you have Zi generates xi, you add some epsilon noise. And the noise itself has mean 0, covariance psi. And the covariance, I assume it's diagonal. Okay, for simplicity, the prior distribution of the latent variable, which is QZI, do you remember, can be assumed to be multivariate Gaussian distribution. So factor analysis assumes, for simplicity, that it's multivariate Gaussian distribution. So P of Zi, you can write it as N, which is the normal distribution, Gaussian distribution of Zi with these parameters, mu 0 and sigma 0. Okay. So I can, this is a PDF, probability density function for Gaussian distribution. And mu0 and sigma, mu0 is the mean, p dimensional, sigma 0 is a covariance matrix of Zi, p by p, right? Don't confuse it with the covariance matrix of noise, which was psi. Okay. Now xi, as we said, is obtained by 3 steps: linear projection of Zi by lambda, which is d by p. So lambda is d by p. Zi is p. So lambda Zi becomes d by 1, right? And mu is also, did I make a mistake? Give me a second. Yeah, I think I'm right. D. Yeah, I'm right. Mu is d by 1. Mu is d by 1. Don't confuse this mu with mu0. I just confused that in my mind. So mu is different from mu0. Mu0 is p dimensional, but mu is d dimensional. Okay. And psi is also, psi is d by d. Right? So I can write probability of xi given Zi as this. Okay. Hence, the data point xi has a conditional multivariate Gaussian distribution given the latent variable. Okay. And mu, what is mu? It's the mean of data. Why? Can you tell me? Can you please tell me why is mu the mean of data? What was Zi? Latent, right? So lambda Zi, I assume it gives me some, so Zi is some latent factor. With some transformation, linear projection, it gives me data. However, I need to add the mean of that. So its mean is 0. I need to add the mean mu to reconstruct the mean of the data. And I know that the mean of the noise is also 0. Right? The mean of the noise is 0. Therefore, see, the mean of the noise, it was 0. We will see it in more detail. We will see it in more detail. Okay. Why do I set the mean of noise to be 0? Because I don't want to change the mean of data. If you have non-zero mean of noise, you will change the mean of the data. Okay. Then, so the marginal distribution of xi. What do I mean by marginal distribution? It means that I integrate over all of the zi's, which is right. Integrate the probability given probability of xi given zi times p of zi dzi. This is equivalent to the joint distribution of xi and zi. Right? This part. Okay. Now, p of, this is what I had in the previous slide. Okay. I can marginalize it in this way. So I have these additional variables. So I put them here in this equation that I have. Also z, p of zi, I know its parameters are mu0 and sigma 0. I know that, right? According to equation 14. So I can, give me a second. Here and variance. Okay. Here, guys, please listen to this. This is important. Here, I have this. This is exactly lambda mu0 plus mu. I had what? Lambda zi plus mu. Okay. I had lambda zi plus mu. The mean of zi is mu0. Therefore, the mean after transformation becomes lambda mu0. But I also have mu, right? Therefore, my mean becomes lambda mu0 plus mu. My mean here. What happens to my covariance? I had some sigma here, psi here, sorry, psi, right? I have some psi here. Also, it has some additional covariance, and that will be lambda sigma 0 lambda transpose. Why? Because I had sigma 0 as the covariance of Zi, and I know covariance is quadratic. Therefore, after transformation, it becomes lambda sigma 0 lambda transpose. We had this discussion for PCA also. By the way, I know it's a bit hard to absorb. There is no exam on it. Just try to understand and enjoy it. Okay. These are the hard parts of machine learning. Few people understand these parts. Okay. Try to understand and enjoy it. Then I define this to be mu hat, which is d-dimensional. I also define half of this to be lambda hat. Why do I do that? Because I want to write this part as lambda hat transpose. Okay. Why am I allowed to do this? Why am I allowed to write this as this? Can you tell me? Because I know that sigma 0 is positive semi-definite. Its eigenvalues are non-negative. Therefore, I am allowed to write every element of the diagonal matrix to be square root of that element times the square root of that element. If I knew that the diagonal elements would be negative, I couldn't do that. I know that the diagonal elements of a covariance matrix are either 0 or positive. They are non-negative. Okay. Then what happens? So this is what we had. This is exactly what we talked about in factor analysis. Xi is given as a linear transformation of Zi plus some mu, and that mu is the mean of data plus epsilon, the noise. And I assume that P of Zi is the Gaussian distribution of 0 and I. Okay. Here, as I have said, so for simplicity, as a mean mu hat, I forgot to say this bullet point. As the mean mu hat and the covariance lambda hat are needed to be learned, we can absorb mu 0 and sigma 0 into mu and sigma. Do you agree? So I have mu 0 and sigma 0. I have also mu, the mean of data, and sigma, the covariance of data. Why? I can, when I have one unknown variable times another unknown variable, I can see this multiplication as the third unknown optimization variable, right? Therefore, let's absorb it and ignore that. And I assume that mu 0 is 0 and sigma 0 is I. What do I mean? I assume that in equation 14, the prior of Zi latent factor has mean 0 and covariance identity. It's a standard Gaussian distribution, as you see in equation 20. Equation 21, also we said that let the noise have mean 0 and covariance psi. Okay. Now, the joint distribution of Xi and Zi, I define it. So I define a vector concatenating Xi and Zi, right? Which I think it will be D plus P dimensional, to be a vector Yi. That's also a random variable, right? Because Xi and Zi, we have seen them as random variables. So Yi is also a random variable. Let its mean be mu I and its covariance be sigma I. And as we know that Xi and Zi are both Gaussian, therefore Yi is also Gaussian. Okay, the expectation of Xi, let's see that. Expectation of Xi, according to equation 19, which was the formulation of factor analysis, I replace Xi with what I had here. Expectation is a linear operator. I can apply it on the elements. So this expectation of mu is not a random variable. It's the mean of data. So it becomes mu. And expectation of noise. Expectation of noise means the mean of noise. The mean of noise was 0. So it goes away. Expectation of Zi, we assumed it's also 0. So it goes away. So it becomes mu. Now you understand the philosophy behind this adding mu here. Because I know that the mean of lambda Zi is 0, the mean of epsilon is 0. I need to have the mean of data because xi has some mean. Okay. Therefore, mu y, the mean of y here is the mean of x and mean of z. The mean of z is 0, but the mean of x is mu. Right? Okay, there is a lemma. There is a lemma for joint distribution. So consider two random variables, xi and zi. Xi is d-dimensional, zi is p-dimensional. Let's concatenate them into a vector yi, as we did. Okay. Assume that xi and zi are jointly multivariate Gaussian. Hence, the variable zi has a multivariate Gaussian distribution, which is this, right? This lemma says what are the mean and covariance of yi with respect to the mean and covariance of xi and zi. So here I have three variables, xi, zi, yi. What is the relation of the means and covariances of xi and zi with the means and covariance of yi? Right? This is the, so here, the mean and covariance can be decomposed into this way. In this way. I can decompose it in this way. Okay. And this decomposition also, give me a second. Yes. So another lemma for proofs, by the way, you can see on my tutorial. I haven't brought the proofs, otherwise this lecture would become overwhelming. Okay. So, or you can see the reference 7. So mu of x given z, the mean of x distribution given the z distribution is this. Accept it from me. It's a lemma. Okay. The mean of the covariance of x given z is this. And what are sigma 1, 1, sigma 1, 2, sigma 2, 2, and sigma 1, 2, 1? These are the decomposition of the covariance matrix. Okay. Also, I can write likewise mean of z given x and sigma of z given x. So equation 27 and 28 are the means and covariances of x given z. Equations 29 and 30 are the mean and covariance of z given x. Okay. Now we are going to use these formulas, those formulas in the lemmas. Okay. According to equation 20. So what was equation 20? We know that P of Zi is a standard normal distribution, the latent factor, right? Therefore, sigma 1, 1, sigma 2, 2 is sigma Z is I. Do you understand? When I put them together here, when I put them together in equation 22, I have mu y sigma y, and I said in this lemma, I said sigma y can be decomposed into this. What is sigma 1, 1? That's exactly the sigma of xi. What is sigma 2, 2? That's the sigma of zi. What is sigma 1, 2? That's the covariance between xi and zi. And sigma 2, 1 is the covariance between zi and xi. And that's symmetric, right? Okay. So we know that according to the formula for the distribution of latent variable, I have this. Also, according to equation 19, which was the formula for the factor analysis, sigma 1, 1 is the sigma x is this. Let's calculate sigma x. So sigma x, which is the covariance of x by definition, is the expectation of xi minus mu times xi minus mu transpose. Recall preliminaries. Okay. Then I replace xi with equation 19, the formulation of factor analysis. I have this, also have this. Okay. Now what do? I apply the transpose in on the elements, and then I multiply the terms to each other. I will get this. Okay. Now expectation is a linear operator. I can apply it one by one. And I know that lambda is also not a random variable, so I can bring it out of the expectation. Therefore, I get this. Why am I allowed to write expectation of epsilon zi transpose as expectation of epsilon, expectation of zi transpose? Because epsilon and zi transpose or zi are independent random variables. Okay. What is expectation of epsilon? It is 0. It becomes 0. What is expectation of epsilon here? 0. What is this? This is exactly the covariance of epsilon, the noise, psi. What is this? Covariance of zi. We assume it is identity. So it simplifies to lambda transpose plus psi. Interesting. The covariance of X is lambda transpose plus psi. In this lecture, you should be patient with math. After patience, you will see how interesting it becomes. Okay. Then let's calculate sigma 1, 2. What is that? Sigma of X z between X and Z. By definition, recall preliminaries. That's expectation of Xi minus mu times Zi minus mu 0 transpose. Mu 0 is the mean of Zi, mu is the mean of Xi. We know that mu 0, we assumed it to be 0. I replace Xi with the formulation of Xi in factor analysis, equation 19. And then again, expectation. So I apply this Zi transpose to the elements, and then I know expectation is a linear operator. I apply it on the elements. I know also epsilon and Zi are independent, so I can write it in this way. Expectation of epsilon is 0. This is also 0. This is covariance matrix of Zi, which is identity. Therefore, it became lambda. Interesting. And we know that sigma 2, 1 is sigma 1, 2 transpose, because sigma needs to be covariance needs to be a symmetric matrix. Therefore, we found all elements. This is I. This is lambda transpose plus psi. This is lambda. This is lambda transpose. Right? And the mean of Xi is mu. The mean of Zi is 0. We could find all of the parameter formulas for the joint distribution of Xi and Zi. Interesting. Hence, the marginal distribution of Xi only consider Xi, okay? Or the prior of Xi is this. Why? It means that only consider this first element and this first element is mu and lambda transpose plus psi. This is exactly what we found, okay? Now, according to the lemma that we found, QZI was probability of Zi given Xi, right? And according to the lemma, its parameters are mu of Z given X and sigma of Z given X. According to the lemma, if you put what we found, so these elements, this is sigma 1, 1, this is sigma 1, 2, this is sigma 2, 1, this is sigma 2, 2, this is mu 1, this is mu 2. Put all of these in the formulas of the lemmas. You will get these two equations. Okay? Mu of Z given X and sigma of Z given X. Do you understand what it means? It means that given X, I see the observed variable, the data. I must have some factor, latent factor. What is its mean and covariance? Interesting. Okay. Now recall that the conditional distribution of data given the latent variable, which was P of Xi given Zi, was introduced in equation 15. Right? Do you want me to go back to equation 15? I don't remember equation 15 myself. This was equation 15. We had it. P of Xi given Zi was covariance the Gaussian distribution of lambda Zi plus mu and psi. Okay. Let's go back to where we were. So this is exactly, I'm repeating it here, equation 15, okay? If data are centered, guys, if data are centered, already centered, such as what we did in PCA, we assume that the mean of the data is centered, right? 0. Then mu becomes 0. Then the formulas become simplified. Okay? Then P of xi given lambda and psi becomes this. The mean becomes 0. And also, this becomes 0. So this is simplified to lambda zi. So equation 38 and 39 are the simplified if the mean of data is 0. And you might see it in some papers. Therefore, in some works, people center the data as a pre-processing to factor analysis. Interesting. Now, guys, we found the formulation of factor analysis. Now we found the formulation. Now let's do the optimization to find the parameters. We can find the parameters lambda and psi using expectation maximization, using variational invariance that we talked about, right? See our tutorial factor analysis, probabilistic principal component analysis, variational invariance, and variational autoencoder tutorial and survey for the details of EM steps in factor analysis. I didn't bring the EM steps of factor analysis, otherwise it would be 10 or 15 slides. It would overwhelm you, okay? If you want to see how we do EM for finding lambda and psi, go and see that tutorial. Also, you can see the chapter of variational inference or factor analysis in our book. Now, probabilistic principal component analysis, probabilistic PCA. So we talked about PCA. Most people know what PCA is, but few people know what probabilistic PCA is. You will know that today, okay? What is it? Probabilistic PCA or PPCA, it was proposed in 1997 to 1999. You see how old it is? It is a special case of factor analysis. Did you know that? Did you know that probabilistic PCA is a special case of factor analysis? And what is that? It assumes that the covariance of noise in the factor analysis, it was, in factor analysis, we knew that the covariance is diagonal already, okay? However, it makes an additional assumption. All of the variances and diagonal elements of this covariance matrix are equal. And they are sigma squared. So factor analysis says that the noises of the different dimensions are independent. However, probabilistic PCA says they are independent, but the noises in every direction is the same. Its spread is the same. So the noise is like a hypersphere. Rather than being oval, it's like a sphere. It's called isotropic noise. It's isotropic. In every direction, it's the same value. It's like a hypersphere rather than the hyperoval. Okay. So the probability of noise is simplified to this. It's relaxed. It relaxes the covariance of factor analysis. And again, its probabilistic graphical model is this, as you see. The difference is this. Okay. Again, as PPCA, probabilistic PCA, is a special case of factor analysis, it is also solved. It can also be solved using expectation maximization. However, interesting thing is here. Why did we relax it? Why did we relax factor analysis? And we named it a new algorithm. Why? Because it simplifies the solution. Do you remember? I have said it multiple times in this course. In this world, whatever you get, you lose something. Whatever you lose, you get something. Okay. Here, we are losing the generality of the noise, but we gain something. The solution becomes closed form. In factor analysis, you need to find the solution iteratively in expectation maximization. You can do it here too. However, you can find a closed form solution for probabilistic PCA. Interesting. You don't need to do it iteratively. It's always a trade-off in machine learning. Okay. So we can have a closed form solution. For EM approach, for probabilistic PCA, see reference 9. For closed form solution to EM approach, see reference 10. Okay. So its solution becomes simpler and in closed form. We can find the parameters lambda and sigma using expectation maximization or the closed form solution. And you can see our tutorial paper for seeing how we found it. In the tutorial paper or in the chapter or our book, we have said how you solve the closed form solution. You find the closed form solution for probabilistic PCA. You can see that tutorial. I haven't brought it here not to overwhelm you. Acknowledgement. Some slides are based on our tutorial paper. Again, you can take a look at this. Also, some slides are inspired by the teachings of deep learning course at the Carnegie Mellon University. See their YouTube channel. It's very good. Okay. Also, factor analysis exists in scikit-learn. You can see that. As you see, we are covering almost all of the algorithms in scikit-learn for machine learning. So you can see it. But as you see, factor analysis can be used for dimensional reduction because it's a probabilistic dimensional reduction algorithm. These are the references. Okay, let's have a break. What time is it? Come back at 9. What? Can we come at 9 because we are and thank you. Let's come back at 9. Thank you. Okay, so now we covered most of the spectral dimensional reduction algorithms and probabilistic factor analysis and probabilistic PCA. Now we are going to cover another probabilistic dimensional reduction method, and that's called SNE and t-SNE. So the t-SNE is one of the state-of-the-art algorithms for data visualization. Okay, t-SNE and UMAP, these two are the state-of-the-art nowadays. So let's see. A stochastic neighbor embedding, or SNE, it was proposed in the year 2003. Okay, by who? As far as I remember, by Hinton, and I guess by Royce. You can see reference 1. I don't remember. I think it was Hinton and Royce proposed that, Sam Royce. So what did they say? It's a manifold learning and dimensional reduction method which can be used for feature extraction. Yeah. What? Okay, Hinton and Royce. That's great. So as you see, Hinton did a lot of things. Also, Sam Royce proposed a lot of algorithms. So it has a probabilistic approach. It fits the data in the embedding space locally, again, similar to LLE locally, hoping to preserve the global structure. This was the idea of manifold learning in the head of Sam Royce, right? Okay, the idea of SNE is to consider every point as neighbors of other points with some probability, where the closer points are neighbors with higher probability. What do I mean? Assume here we are some data points in this class. You, which are in the front row, you are closer to me, but you are farther away from me, right? Who is neighbor? You can say you are my neighbor and you are not my neighbor. Yeah, you are far away. However, they said let's not make it binary, neighbor, non-neighbor. Let's make it fuzzy. Let's make it in a way that it's a float value. I score it. He is closer to me, so it's more neighbor to me than you. You are also my neighbor, but with low score, right? And how do I model this score? I model it probabilistically. So I assume I'm a data point. Around me is some Gaussian distribution, and whose mean is me. So every point has some Gaussian distribution whose mean is itself. Okay. Of course, if a point is closer to that point, in the its probability is huge. But the farther you go away from that data point, the less dimensionality you will have. So you can model being neighbor as a probability density function, PDF, right? Okay. Therefore, rather than considering k-nearest neighbors in binary manner, we consider neighbors in a stochastic way. Then what? Okay, we find some probability, we define some probabilities of neighborhood. Then what? Let's find the embedded data points in the low dimensional space in a way that they have the same probability, the similar probability density functions of neighborhood. See, if you are highly probable to be my neighbor in the low dimensional space, you also need to be highly probable to be my neighbor. If you are away from me, so you are low, the probability of being my neighbor is low. In the embedded space also, you should be away from me. Your probability of neighborhood should be low for me. Do you get it? And now I think you understand how we should do this. So we have some PDFs. We also have some PDFs so we have some PDFs in the input space. We have some PDFs in the embedded space. KL divergence, minimize the KL divergence of the idea is interesting. So let's preserve the probability of neighborhoods. I think after this course, you're ready to go and design algorithms. I think if you read more a bit, and now you can read the literature and you can design your own algorithm. Okay. So some examples, there exist some other similar probabilistic dimensionality reduction methods which make use of Gaussian distribution for neighborhood. Some of them were neighborhood component analysis, NCA. I think this also proposed by Hinton, I guess, at time. Deep NCA and proxy NCA. Okay. So NCA was used later in deep learning and as a loss function. SNE, a stochastic neighbor embedding, uses Gaussian distribution for neighbors in both input and embedding spaces. So what? SNE says in input space, I use Gaussian distribution. In the embedding space, I use Gaussian distribution. I want the KL divergences between these two to be minimized. However, t-SNE, which we'll see later, who said that we should use the same distributions in the input space and embedding space? Who said that? I can use some distribution in the input space, some other distribution in the embedding space, and then minimize the KL divergence between them. Okay. But why? What's the justification for using another distribution in the embedding space? Guys, I need to focus. What is the justification for using another distribution in the embedded space for t-SNE? We will see. We will see. There is a nice justification for that. And so t-SNE uses Gaussian distribution in the input space, but in the embedded space, it uses a student t distribution. Hence the name t-SNE or t-SNE. T is borrowed from a student t distribution. Okay, t-SNE. It's called t-SNE or t-SNE, or it uses student t and Gaussian distributions. By the way, I apologize. t-SNE uses t distribution in the input space, Gaussian distribution in the embedded space. I apologize. Okay, I said it the other way around. Doesn't matter. It uses different distributions in the input and embedded space. What? No, nice. The student t distribution is we have several distributions, such as gamma distribution, beta distribution. A student t distribution is one of the distributions whose special case is Cauchy distribution. No, we will see that. We will see what t distribution is. So it's one of the distributions. Okay, t-SNE is one of the state-of-the-art methods for data visualization. For example, it has been used for DNA and single-cell data visualization. Why? Why is visualization very important for DNA analysis and gene analysis in biotechnology? because it's very important for them to find similar DNA, similar genes for drug discovery and these things, right? That's why these methods are very especially developed for DNA analysis. Okay. The goal of and the dimensionality of DNA is huge. So they want to see it in visually in 2D, right? The goal of SNE is to embed the high dimensional data, x1 to xn, each of which is d-dimensional, into the lower dimensional data. So yi is the embedding of xi. It's not labeled, it's embedding. N is the number of points. The dimensionality of input space is d, dimensionality of the embedding space is p. Okay, and we usually have p much less than d. For data visualization, we take p to be 2 or 3, right? A 2D visualization or 3D visualization. Let's go into the mathematics now. SNE. SNE proposed in 2003, we consider a Gaussian distribution around every point xi, where the distribution for probability of accepting any other point as a neighbor of xi, right? The farther points are neighbors with less probability, of course. Okay, this is the Gaussian probability that we can use. What is d here? Here, d is distance from the data point. Okay. The fixed multiplier, so we have a multiplier. This is the normalization factor, right? We can drop it. We can drop it for the sake of optimization, okay? However, if we drop that, this doesn't sum to 1, or this doesn't integrate to 1, right? That it won't behave like a probability. If we drop the constant multiplier, the normalization factor, it doesn't sum to 1. So we use a technique that we have seen a lot in machine learning. It's called softmax. So this is Gaussian distribution without the normalization factor, right? So we sum over all of the points in the denominator to make it to sum to 1, right? It sums to 1. And Pij is the probability that xi accepts xj as its neighbor. Okay, so Pij, it says whether the probability that xi takes xj as its neighbor is this. It's a scalar, and I write it as exp of minus dij squared. Dij squared is this. What is this? This is squared Euclidean distance between xi and xj with some normalization factor, 2 sigma I squared, exactly as we have in the Gaussian distribution, right? However, in the denominator, I need to normalize it, so it sums to 1. And here I say I sum over all of them except k not equal to I. Why? Because I don't want to calculate the distance of me to myself. It will be 0, but doesn't matter. I don't want to have additional +1 in the denominator. Okay. This sigma I, the variance in the distance, can be found. It is a hyperparameter. You can either set it to be a fixed value, or you can find it by binary search. Doesn't matter. Okay. It's not that much important. So Pij that we saw in equation 2 is the probability of neighborhood in the input space, d-dimensional input space. Now let's calculate the probability in the embedding space. We denote it by Qij. That's defined similarly, very similar to Pij, but we have Zij squared rather than Dij squared. And Zij squared is the squared Euclidean distance between the embedded points of Yi and Yj, right? Okay, here I have dropped, so here in Dij squared, I have 2 sigma I squared. However, in the Zij squared, I don't have any sigma. Why? There is a reason behind it. Because in the input space, the density of points differs in the space. Sometimes we have dense areas, sometimes we don't have dense areas. We need to adjust the probability. However, in the embedding space, we are finding yi and yj. So we can absorb sigma into it. We are initializing yi and yj, and we are finding yi and yj. So we don't need sigma in the embedding space. Okay. If you say this, I have two probabilities, I want them to be similar to each other. If you say to a baby, what would they say to you? Minimize their K divergence, right? So this is K divergence between Pi and Qi, Pij and Qij's. This is the definition, the discrete definition of K divergence. Okay. Why am I using discrete? Because I have endpoints. It's discrete. Okay. This is the cost. We need to minimize it. We don't have any constraints here. How do we solve it? Take derivative, set it to 0. If you find a closed form solution, done. If not, what do you do? Iteratively, for example, using gradient descent. Or Newton's method, gradient descent. They use, I think, gradient descent, yes. This is a gradient of this cost with respect to yi. The optimization variable is yi for all I from 1 to n. Here it is. So there are 3 costs in this lecture. For the first 2, I don't bring the proof. I refer you to my tutorial paper for the proofs. But for the third one, which is the most important one, t-SNE, I will provide the proof here. Okay. For proof of this, see our tutorial, stochastic neighbor embedding with Gaussian and a student t-distributions tutorial and survey, or our textbook. Okay. By the way, this derivative is a p-dimensional vector. Why? Because it's a derivative of a scalar with respect to a vector, and yi is p-dimensional. And you can use gradient descent in order to find update yi until convergence, right? Of course, you need to do some initialization. And now you understand, based on every initialization you end up with different embedding, right? And PII here in this case, I assume PII and QII, I let them be 0. I don't want to consider them, okay? So as I said, we can use gradient descent. What did Hinton do? Hinton and Sam Royce, they used gradient descent with momentum. With momentum. Why did they use momentum? Because they didn't want to have oscillation in their solution. For more information, see my optimization course, why we use momentum. So this is exactly gradient descent with momentum. Okay, this alpha t is a momentum term. This is a momentum term. And we can, for initial iterations, we can have a smaller momentum because we want to first update the solutions rapidly. After a while, we increase the momentum. So we don't, because we are close to the solution, we don't want to have oscillation. So until iteration 250, they had half as alpha. After that, they set alpha to 0.8. Okay, eta is the learning rate. They used 0.1. And also, we should add some Gaussian noise or random jitter to the solution of the first iterations before going to the next iterations. It helps avoiding the local optimum. Apparently, Hinton and Sam Royce, I think Hinton was professor at that time. Sam Royce was, I guess he's a student. So Sam Royce went and coded the idea that they had. They saw that it's not working well. It should work well theoretically. So in practice, it didn't work well. They said some hacks. Let's do some techniques. Let's add some random noise to it in initial iterations. And then they saw it works well. So this is just some heuristics that they tried. Okay, SNE is over. The second thing is symmetric SNE. In symmetric SNE, it was proposed in 2008. In this, I think in the same paper of t-SNE. Okay, what does it do? We consider a Gaussian probability around every point xi, and this probability is this. Okay. Do you see the difference? What is the difference of equation 10 and what we had of as Pij in SNE? The difference is very tiny, is here. This is L, this is dkl. In the denominator, in SNE, we had summation of ext minus dki squared for k, for all of k's which are not equal to I. Am I right? Yeah. However, here we have L. The difference is that here with sum over all of the pairs, However, in SNE, we sum over all of the pairs excluding the pairs which have I in it. Right? Why do we do that? The problem here in SNE was that it wasn't symmetric for Pij. So Pij was not equal to Pji. Here, Pij becomes symmetric. Right? Do you agree? In SNE, that we had I in the denominator, then Pij wouldn't be equal to Pji. Because the denominator would differ. Although Dij would be similar, although Dij in SNE also is symmetric, but denominator would make a problem for us to be symmetric. Okay, so they changed that, Pij to become symmetric. And yeah, so this is exactly what we had in SNE. We compare these two. Okay, so this is what they had, and however, there is a problem with this. However, okay, this is symmetric SNE, but there is another problem. So the problem of non-symmetric is resolved. Now another problem occurred. What is that? The problem with outliers. Why? If the point xi is an outlier, its Pij will be extremely small. Why? Because the denominator is fixed. Here the denominator is fixed, right? For all of the ij's. But the numerator will be very small for an outlier, very far anomaly, right? Very far away. However, in SNE, the denominator would be also small. Then the denominator would be small, the numerator would be small, so the whole thing the fraction wouldn't become very small. However, in the symmetric SNE, we have a problem with outliers. It becomes too small. When I say too small, it means that in computer it rounds to 0. Okay, so they propose another idea. They said, okay, let this be Pj given I. This equation, I name it Pj given I. I also calculate Pi given J. Sorry, this is what we had in SNE. This is what we had in SNE. Okay, so it has I in it. Okay. Let what I had in SNE, let it call Pji given I. Also Pi given J. I have, these are not equal to each other because this SNE was not symmetric, right? Now I define Pij, which is symmetric, as the average of Pi given J and Pj given I over 2n, right? This is the average of them. Okay, so this is the second variant for symmetric SNE, and it works well. Also, it works well for outliers. So they use this equation 12. Okay. So also in the embedding space, we use this first variant. We don't have the problem of outliers in the embedding space anymore. Why? Because we initialize the embedding points ourselves. We update them ourselves. There is no outlier in the embeddings. Okay, so we are allowed to use this Qij as a symmetric Qij in the embedded space. Okay, again, KL divergence between them, and this is its derivative. Note that the derivative differs now from SNE. The derivative differs. For the proof of this, see our tutorial paper. By the way, the proof of SNE and symmetric SNE do not exist in the literature, as far as I know, at least several years ago. I saw the proof of t-SNE in the paper of t-SNE Then inspired by that, I tried to find out what Hinton did on their paper. It's very interesting. Go and see the paper of S&E, which was published in 2003 in NIPS conference. Hinton says in the manuscript, the proof is too complicated and I don't bring it in the in the paper. And they didn't have any supplementary material or appendix also. I couldn't find the proof anywhere. And I wanted to write the book. So I had to write the proof. What did I do? I went and saw the proof in t-SNE paper. Inspired by that, I tried to replicate what Hinton had in mind. And you can see the proofs of S&E and symmetric S&E in our tutorial paper, as well as our textbook. Okay. Now, t-distributed, give me a second. Now, t-distributed stochastic neighbor embedding, or t-SNE in short. What is it? In S&E, we are considering Gaussian distribution for both input and embedded spaces, right? Which is what we saw. That is okay for input space because it is already in high dimensionality. However, when we embed the high dimensional data into a low dimensional space, there is a problem. Let me, rather than before seeing that slide, listen to my story. Okay. Assume I have 10 people. I have this room. Can I fit the 10 people here? Of course I can. We can easily choose where to sit. Assume now I have 1 million people. I want to fit them in this room. Can I do that? Of course, they don't fit here. How can I fit them here? So I have to do it. How can I fit 1 million people in this room? No. So it might seem stupid to you, but listen to me. How can I fit 1 million people here? Let's enlarge the room. Assume I can. Assume I enlarge the room. I move the walls. I enlarge the room. I enlarge the room until I can fit 1 million people. This is the simple idea of t-SNE. t-SNE, some person named then Martin, something like that, if I can pronounce his name correctly. He's now a professor, I think, in Netherlands. He was a student of Hinton in University of Toronto. Okay. This is the idea that they had in their mind at that time. They said, there is a problem with S&E. S&E uses Gaussian distribution in the input space and in the embedded space. In the input space, I have huge dimensionality. In the embedded space, my dimensionality is very low, such as 2 or 3, right? And here, assume dimensionality is the number of people. Dimensionality is information. When I say 1 million people, it means that 1 million dimension or a lot of information. How can I fit a lot of information into low dimensional space, which I can't fit it? I will destroy some of the information. So what do? Let's enlarge it, the room in the embedded space. Okay. In the embedded space, I need to enlarge the room. Okay, how do I do it mathematically? You tell me. S&E uses Gaussian distribution in the input space and in the embedded space. But t-SNE says I want to enlarge the room in the embedded space so I can fit the information of high dimensional space here. How can I do that? Let's change the distribution. Okay, let's use a distribution which has heavier tails. So assume this is the Gaussian distribution. I want to use similar distribution, so the distribution shouldn't drastically change. But I want to have heavier tails. Why? Because it's exactly like enlarging the room to fit more information. What is very similar to Gaussian distribution but has heavier tails, goes to 0 slowly, more slowly, is t-distribution, the student t. Student t distribution. Okay, this is Gaussian distribution. The reason they name it the student T is because the paper which proposed that, the author named himself a student as a nickname. Okay, that's the reason. So, where were we? Okay, so as this is exact, and this problem that I told you is called the crowding problem. The crowding problem. There is a crowd, I can't fit it here. And you can see this room, I'm enlarging the room here. Okay, so the main idea of t-SNE, which was proposed in 2008 in Journal of Machine Learning Research, is addressing the crowding problem, which exists in SNE. Okay, so we use a student T distribution rather than Gaussian distribution for low dimensional embedded space. Okay, it has heavier tails. So this is for Qij in t-SNE, I use this. Okay, this is Qij. What is this? This is a standard Cauchy distribution. This is a standard Cauchy distribution. Okay, equation 18. It's a special case of a student T distribution. t-SNE uses this, which is a special case of a student T distribution. Okay, and what is that? What does it? So you can write it in this way, right? 1 over p, 1 plus z squared minus 1 over p is the normalization factor. Drop it as we did it before. You have this, but it doesn't sum to 1. So you have to use the softmax technique again, right? So you have this, and you use the softmax technique. And what is Zij? The distance, the Euclidean distance between Yi and Yj. You asked me what is a student T distribution. This is a student. Equation 19 is a student T distribution. It's complicated. It has gamma function. Gamma is a gamma function. If you don't know what gamma function is, look it up in Wikipedia. Okay, so, and it has degree of freedom. Gamma function has a degree of freedom, delta. Okay, if we get rid of the constant normalization factor, we can write Qij in this way. Okay, if you set delta to 1, you will get what you had here in t-SNE, original t-SNE. So Cauchy distribution is a student T distribution with 1 degree of freedom. Okay, now that's why the original t-SNE, we can call it Cauchy SNE because it uses Cauchy distribution. Later papers, they proposed t-SNE with general degrees of freedom. Okay, but original t-SNE is Cauchy SNE. So they use, for input space, they use the same idea as symmetric SNE. So they have Pij, Gaussian distribution, but they make it symmetric. Okay, then in the embedded space, they use Cauchy distribution or the student T distribution with 1 degree of freedom. Right? Again, we have 2 distributions. Let's minimize the KL divergence. So I have, this is the KL divergence between them. And if we take derivative, this is a derivative of this cost function, equation 26. Now we are going to prove that. Also, it's provided in my tutorial. But here we are also assuming Pii and Qii is 0. Okay, let's prove it to see the beauty. Proof here is according to the paper of t-SNE, but a little bit modified. Let Rij, I define it to be Zij squared. So this is Zij squared, Yi minus Yj, Euclidean distance squared. This is a scalar, right? Now by changing Yi, if I change Yi, we only have change impact in Zij and Zji for all j's. Do you agree? Assume in the embedded space, I change Yi. I'm taking
taking derivative with respect to yi, right? So according to the definition of derivative, I should change yi and see what is impacted. So if I change yi, zij and zji changes for all j's. Okay. So according to the chain rule, I can write derivative of C3, which was the cost with respect to yi, is the derivative of C3 with respect to Rij times derivative of Rij with respect to yi, plus derivative of C3 with respect to Rji times derivative of Rji with respect to yi. And I sum over all of the j's, right? Okay, according to this equation 28, this is Rij, right? Rij, equation 28. Now let's calculate these derivatives. Derivative of Rij, this one. Derivative of Rij with respect to yi. What is that? It becomes 2yi minus yj, because this is quadratic with respect to yi and yj. Okay? Rji, it's according to equation 28, is squared Euclidean distance between yj and yi, but Euclidean distance is symmetric. I can write it again back as squared Euclidean distance between yi and yj. So its derivative is the same as before. Okay. Therefore, if you put these two in this equation, it simplifies to this. You can factor out yi minus yj. Okay. So now we have these two derivatives which we need to compute. The cost function which we had, C3, can be rewritten as this. How? Here I have summation over k, again summation over L, which is not equal to k. So I can absorb these two summations and write it in as one summation of k not equal to L. Okay. And then, so by this I mean two summations. Okay. Then I can write this logarithm as logarithm of numerator minus logarithm of denominator. So I will get this. The first term is constant with respect to QKL, and thus to RKL. So this is the first term. If you change the optimization variable yi, does it change PKL? Does it change? You please tell me, guys. If I change optimization variable, does it change the first term? No, the first term is the probabilities in the input space. It's fixed, right? So I can drop it. Therefore, its derivative with respect to Rij, see here. I'm calculating this. With respect to Rij, the first term goes away and I only have the second term. Okay. According to equation 24, this was equation 24. Do you remember? This was the Qij, the Cauchy distribution in the embedded space. QA, now I replace I and J with K and L to write QKL. Does it matter? It's a dummy variable. I and J are dummy variables. I change the names of indices, and K not equal to L, I change it M not equal to F. Okay, guys, listen, this is important. And then what happens? I rewrite ZKL squared as RKL, ZMF squared as RMF, right? Of course. Okay, now I define the denominator, I call it beta. Then this is beta, or this, right? Let's see what happens. The derivative which we wanted to calculate is this. We had this. I'm repeating what we had. Also, this is QAL and this is beta. Let's use them all here. We have logarithm of QKL equals logarithm of QKL plus log of beta minus log of beta, right? This equals this plus something minus that thing, right? Then I can absorb these two together. So I can write it as logarithm of QKL beta minus logarithm of beta, right? Therefore, now here in derivative of C3 with respect to Rij, I had this term, which I just simplified, this term, right? So I replaced this term with what I found. Okay. Then this fraction can be broken into these two fractions, right? What happens? What is this? The first term, derivative of logarithm. The formula for the derivative of logarithm is this. This is the argument of logarithm, 1 over argument of logarithm. Then chain rule, derivative of argument of logarithm with respect to Rij. What is this again? The derivative of logarithm. It's this, right? Okay. Then what do we have? Here, derivative, I have derivative of QKL beta with respect to Rij. So let's simplify QKL beta. So this was QKL, which we found here in the previous slide. This is beta, right? These two cancel each other. Therefore, QKL beta is just a numerator, right? Now let's calculate that. Therefore, I replace this here with what I found here. So it gives me this. Okay, I'm simplifying the derivative for you to find what we want. Okay, we found this. Then we have this derivative of this term. This term, how do we calculate this derivative? Can you tell me? With respect to Rij. So derivative of 1 plus RKL inverse with respect to Rij. It's always 0. And it's non-zero only for if K equals I, L equals J. Right? Because compare these two. For if K is not equal to I and L is not equal to J, it's some other thing rather than Rij. And it's constant with respect to Rij. Okay. Therefore, I can replace this RKL with Rij. Other terms are 0. And then this derivative is this. This is the derivative, simple derivative formula. Okay. Then now let's calculate this term, derivative of beta with respect to Rij. This is beta. Again, for the same explanation, I replace RMF with Rij, and its derivative is this. Okay. So now let's put back what we found. We found this. So see what I'm doing. What am I doing? By the way, this summation goes away. Why? Can you tell me? We just discussed it here. It's non-zero only for K equals I and L equals J. Therefore, the summation goes away. And KL becomes IJ for the discussion we had. This QKL becomes QIJ for the discussion we had. This is beta here. This, we just calculated that here. I'm replacing it here. And the minus also is here, right? And what happens? And their other terms are 0. And also for this term, we just found that it's this. Okay. Can you tell me why didn't the summation go away for this second term? Should understand every step for you to completely absorb the algorithm. So this summation went away for the first term, which was this. For the second term, the summation is still here. Why? Because the summation for this one was already in beta. Summation of beta went away. But the summation of this doesn't go away. Don't confuse this. For the first term, the summation, we had it. But the discussion we had is for the summation in beta, for the second term. Therefore, we still have the summation, the first summation. Okay. Now, what happens? we know that we have P summation of PKL for all K and L equals 1, right? The probability, if you sum all of the probabilities, equals 1. Thus, what happens? What happens? So this, I'm repeating it here. And can you tell me, can I bring this out of the summation? Of course I can. This is Rij, not KRKL. The summation is over K and L, so I can bring it out of the summation. Therefore, I have summation of PKL only, and that is 1. So it becomes this. Then what happens? Then what happens? Then I can, let me think. Exactly. We are factoring out 1 plus Rij inverse. We are factoring it out and we will get this, okay? Then, interestingly, what we find here is Qij. It's exactly Qij. Recall this. No, recall this. Give me a second. Yeah, recall this. Recall this. It's exactly Qij. Okay? So I can and this Qij is cancelled with this Qij here and also multiplied to this one. Therefore, it's simplified to this. Did you see how we simplify the derivative of C3 with respect to Rij? This was one of the derivatives in the term. So this is what we found. Likewise, we can find the derivative of C3 with respect to Rji. So this was Rij, and for Rji, we need to change the order of Ij's. We'll get this, right? And we know that Pij and Pj they are symmetric because we made them symmetric. Therefore, also Qij and Qji are symmetric. Therefore, I can replace this with this. Pji minus Qji with Pij minus Qij. And also Rij and Rji are also symmetric. So I can replace it here too. Okay, so these two, interestingly, are equal to each other. What was our derivative? It was this. Recall equation 29. These two we just found and they were equal. Okay, therefore, I have 2 times this and also have 1, 2. Sorry, I have 1, 2 here. 2 times 2 becomes 4. And also the rest of the terms is as before, right? I just put these 2 here. Gives me this. This is exactly the derivative which we found. QED. Found. Okay, we found it. And now I think you understand why Hinton said it's too complicated to bring it into paper. Okay. SNE and symmetric SNE have the same similar proofs, a bit different, but okay. Just give me a few more minutes to finish. The update of the embedded points. Now we use, again, gradient descent with momentum. With momentum. Here, interestingly, in t-SNE, we don't need to add jitter anymore to the initial iterations because they found that it is more robust than SNE. Okay. In t-SNE, it is better. Okay, there is also a heuristic in t-SNE. And what is that? In practice, they found out that it's better to multiply all Pij's by a constant, such as 4, in the initial iterations. In the initial iterations, they do this. Why? Can you tell me without reading this paragraph? Why? Okay. Because in the initial iterations, I want to focus more on the large probabilities. What if I do this? Can you tell me what happens? If Pij is a small, if times 4, it's also is still small. What if Pij is big? Times 4, it becomes much bigger. So this multiplication by 4 has more impact on large Pij's. Then it means that in initial iterations, I want to focus on nearby or close by points. But after some iterations, then I use the original Pij's. Initially, let me help optimization by this heuristic, by saying that focus more on the close by points. In other words, fit locally. Fit locally. This is called early exaggeration. Early exaggeration. We exaggerate it early. What? Alpha? Yeah, I think they used the similar momentum. We can have general degrees of freedom for a student distribution in t-SNE. Then Qij is changed to this. Qij, which was simple, is if you set delta to 1, you will get the Qij in the original t-SNE. Okay. If you limit delta to infinity, what happens? A student distribution becomes Gaussian distribution. Then t-SNE becomes similar to SNE. So t-SNE uses delta equals 1, original t-SNE. If you limit delta to infinite, it becomes SNE algorithm. Okay. This is an example of the embedding in t-SNE. So they have used applied t-SNE on digit data set from 0 to 9. Do you see what happens? Isn't it interesting? Isn't it interesting that you have something like this? So the points have been kind of clustered. Why? Why does this happen? Because I'm pushing the close by points to each other by optimization, right? In the embedded. And here, the dimensionality of embedded space is 2. Can you see? The D, what is D? The dimensionality of input space is the number of pixels in the image. So assume they have images like this. 1, 1, multiple ones with different rotations and translations, multiple 2s, even 4. Some of them are like this, some of them are like this. Okay, they have different variants of digits and they push them to each other and interestingly, see what happens. They fall close to each other. Very interesting. Acknowledgement. Some slides are based on our tutorial paper, stochastic neighbor embedding with Gaussian and student distributions. Also, you can see it in our textbook. For more information on SNE and t-SNE, see our tutorial paper. Some slides are inspired by teachings of Professor Ali Qudsi at the University of Waterloo. I have coded SNE and t-SNE. You can find it in my GitHub. Also, t-SNE in scikit-learn. You can find it t-SNE in scikit-learn here. And these are the references. As you see, Sam Ruiz is a lot in these references. Okay, so by the way, in industry, whenever you train some neural network, they usually, in order to show how neural network is working, you can use t-SNE. You can get the feature maps of the neural network. It's huge dimensionality, right? And apply t-SNE and see what happens. For different inputs, you get different feature maps, right? You can see them as data points and then apply t-SNE on them and see whether the similar or the points in the same class, do they fall close to each other? If yes, it means that the neural network has done a good job, right? Or whenever, or it is also good for clustering. If you have some data points in industry, especially, you want to do clustering, but you want to do it clustering by visual. You apply t-SNE on your data, and you'll see where the points fall close to each other, and then you can do it clustering by visual. Very interesting. So yeah, next session will cover UMAP, another state-of-the-art method for data visualization, and also we'll go to hidden Markov model. Yes, you have a question. I didn't go. This is I took this image from a thesis, but I can say there are a lot of these figures in the internet. I don't know what the parameters they use, but yeah, there are some default parameters for t-SNE in scikit-learn. You can see that. But usually they use original t-SNE, where they set delta to 1. Yeah. Why? Because it's the opposite way of SNE. SNE is worse for crowding problem, so they want to be opposite of SNE. So they use t-SNE. That's it. By the way, please come earlier at the start of the class. It was only 2 students in the class. But and I thought that people are not coming after midterm or something like that. Please come here. Yeah, okay. That's okay. Thank you, guys. Okay, thanks. Any question? No? Okay, great. Okay.